Alright, so the next family of differential equations we want to look at are actually second order differential equations. So the general um, form, I guess, is a differential equation that involves x's, of course, that's our independent variable, y's, y primes and y double primes, and of course those y prime and y double primes are all linear, so none of them are squared or to any strange power. They are just to the first power, and that's what a second order differential equation will contain, those pieces. Now we're not just going to look at second order differential equations, we're going to look at a subclass of those called reducible second order differential equations, and these are differential equations that can be reduced from second order to first order, and we have already developed some tools for solving first order differential equations. So we'll reduce these from second order to first order. Now we have some caveats. The first caveat is we want to look at the situations, the only ones that are reducible are ones that are second order differential equations that, number one, might be missing the y term. So there is no y term in there. Okay, we've got x's, we've got y primes and y double primes. Okay, those are the easiest and those are the ones we'll look at first. But in order to be reducible, we can't have a y in there. And then the second family are ones that are missing the x term. So they may contain a y prime, and a y double prime. And those, we'll also look at those. So there is no fancy stop sign. There is no x term. Both of those should be reducible. And then once they're reducible, hopefully we can solve them using one of the techniques that we have gone through, whether it be just integration, whether it be using separation of variables or an integrating factor, or whether it turns into something that we can use a substitution method on, or it's an exact equation, right? We've got a few tools that will work. So let's deal with those second order differential equations that are missing the y term. Okay, so the first ones are those that are missing the y term. So let's look at an example here. So let's just play with this one. X y double prime, there's our second order term, and our x term, plus 2y prime equals 6x. So you look at that, you see your x's, you see your y primes, and you see your y double primes. You don't see any y terms. All right. So to reduce these to a first order equation, we make a fairly simple and straightforward substitution. We let p equal y prime. Not y double prime, just y prime. And then that of course means p prime is equal to y double prime. Right? And so once we do that, we get the equation that looks like this. X, instead of y prime, we put p prime, plus 2. Instead of y prime, we put p, equals 6x. And there it is in our reduced form. So once you're here, then you got to decide how you're going to solve it, right? And so we kind of go through our processes, our steps. You know, can we separate the variables? Well, no, because differential equations that have both the prime and the p and the p prime probably not going to be separable, right? And so then we look and say, okay, is this linear, and can it be approached or solved using an integrating factor? And in fact, that's going to work. Looks like that's going to work, because remember, if you get rid of you can't have a coefficient on the derivative, on the prime term, right? And so if we divide everything by that x, we end up with, well, let's try that again. We end up with p prime plus 2 over xp equals 6. And that is exactly the form that we need for an integrating factor. So our integrating factor, rho, is equal to e raised to the integral of 2 over x dx, which turns into e raised to the integral of, well, it'll be 2 times the integral of dx over x, that's ln of x, which turns into e to the ln of x squared, just adding that extra step so we can remember, which turns into x squared. So that's our integrating factor. So if we hit both sides of this thing with the integrating factor, right, then we should be able to solve this thing moving forward. Okay, of course the left-hand side, we know what that is going to be, right? The left-hand side, we immediately know, oh, well, that's just the derivative of our integrating factor times p. Right? We're not differentiating both sides. And then, of course, this right-hand side is just 6x squared. So if I want to solve that, I will just integrate both sides. And that will lead me to x squared p equals, what's this? 2x cubed plus c, right? 2x cubed plus c. And then dividing everything across, we get p equals, what will it be? 2 over x plus c over x squared. Okay, but now remember, this is equal to this right here, right? So we say, oh, well, that's not our solution, that's y prime. Okay, so we are going to need to integrate that to find what y is. So y will equal the integral of 2x plus c over x squared dx. And that turns into y, which is our solution, is x squared plus, let's see, that's going to be, actually put it like this, minus 1/3. Oops, we'll back that up. Let's get that right. X squared, so it'll be what? Minus c over x to the first power plus a different c. Okay, so we get it to looking like that right there, and there's our family of solutions. Now this is going to have, since it's a second order, it's going to have two parameters, right? We call these parameters, right? It's going to have two of those things that are going to be able to take on various values. And if this was an initial value problem, you'd have to have a couple initial starting points in order to figure out what the solution to this, what the particular solution was. But you can see that we reduced it by making a fairly straightforward substitution. But this only works if you're missing that y term. So let's look at the situation, case 2, where you're missing just the x term and so what you have is a differential equation that does include y and y prime and y double prime. This will also be reducible, but it's going to take a little bit of additional work for us to complete. So to attack this one, we will approach it in a kind of similar way. We'll start by letting, we'll just make the substitution, let p equal y prime, and that, of course, that's dy dx. And then that means that that y double prime is the derivative of p with respect to x, of course. But p is a function of y as well as x, so we have to use the chain rule. So in order to find derivative of p with respect to x, we first take the derivative of p with respect to y, and then we using the chain rule, do derivative of y with respect to x. So of course dy dx is, let's put this right here, this is just p. So this turns into, I wrote that down so they can just change the order, p dp dy. All right, so those are the substitutions that we're going to make. All right, so that's going to leave us with just y, as we said, and then y double prime is p dp dy equals y prime squared, which is p squared. Right, now notice this is not a linear equation this is not a linear equation, but we're still able to reduce it. Now looking at this one, we can definitely separate the variables here, right? We can do it in, let's move all the p's to the left and all the y's to the right, and when we do that, when we separate the variables, because it's reduced now to a first order, when we separate all the variables, we're going to end up with dp over p. That's all that's left on of the p's, and then when we move the y's over, it's going to be dy over y. That's it. Okay, that's ready to integrate, leaving just ln of p equals ln of y, and we've seen this trick before. We would normally just put a constant there, but to make our lives a little easier, we'll write it as ln of c, so that this all told becomes, well, we'll add the line here, ln of p equals ln of cy, exponentiate both sides, so that so that p equals cy, where c is just our constant. Okay. Now we don't want p, we want ultimately what y. So here we make kind of an odd, we take kind of an odd approach, because what we have down here, this is just, those are all functions of y. All right, so those are all y terms. And we're going to use a little rule. If I want x as a function of y, I can find that by integrating dx dy with respect to dy. Okay, now so you can follow through this on the book and see what happens. But here's what this leads to. It leads to this is the same as 1 over dy dx with respect to y, or we know what dy dx is, that's p. And so in the end, if you want to figure out what x is as a function of y, you need to integrate this. So in this particular process, once you find what p is, you're going to go to this next step to figure out what x is. And so that's where we would go. We'd say, okay, x is going to be the integral of 1 over cy dy. All right, x is going to equal the integral of 1 over cy. We can move that c up to be with the x, and then that becomes ln of y. Okay, ln of y plus c. Now this is a new c because the original c was already part of the whole expression. Okay, and now this gives us the ability to solve for y as a function of x, right? We'll just squeeze it in here. Y is equal to e raised to the cx minus c sub 1. Okay, or cleaning it up at e to the minus c, we just call it c sub 2 e to the cx. Okay, as our final solution. So it's a little bit different, especially this little jump right here. You might take a little look at that. Once you solve for p, then the way you figure out, the way you work back to your function is using this little procedure in the box. and going from there.